Well, hello, folks. Today we're looking at Leetcode 42, trapping rainwater. Now, you'll notice I just said trapping rain because you know what rain is? It's freaking water, Leetcode. You don't need to say that we're trapping rainwater, right? It's kind of like ATM machine. The M stands for machine. And what was the other thing? Like Tai Chi? No, Chai tea. Chai means tea. What's going on? Okay, I'm going to calm it down for a second here. Let's talk about this one. All right, this is marked as a hard. And I think the only reason it's marked that way is because we can wrap ourselves around it thinking of like super clever ways to solve it. And in reality, it's not that complicated. We're going to do this. We're actually just going to use 2 pointers as with a lot of these problems. But first, let's kind of go over what we're seeing. Now, they have a great example here. And I don't know if you can tell by looking at my handwriting, I am quite an accomplished artist. So what I'm going to do, I'm going to do you a favor. I'm going to draw what they have on the screen right here. So we got the X and the Y axis, and we got here are our walls. There we go. And this is not to scale, unfortunately. So, oh yeah, that's good. So it goes down and then boom. And then, you know what? Let's just leave it like that because we're going to talk about this. So what we're looking for, and I'm going to go ahead and grab a blue, or what color is this? Let's see. Does it not say a name? Oh, that's weird. Markers used to say the name, or at least what they smelled like. Like this one is maple syrup. Apparently this one is electrical fire. So anyway, I'm going to use electrical fire here to signify water. And maybe we'll use a red also to signify where we can't have water. So, quick question before we even start. Can we have water at every single point in this graph? Is it their potential to have water? Well, of course, the answer is no. And I'm going to show you why. Can we have water here? Never, because there's no left wall. So this whole area can never hold water all the way up to infinity. Same thing with the right side, because there's no right wall. So these 2 places can never hold water. So I don't know if that's important or not, but we're just going to point it out. So don't know why I'm out of breath, but I am out of breath just being me. So let's go ahead and look. Let's look at this next spot. Can this spot hold water? No. Obviously, from looking at it, we know it can't. But let's dive into why it can't, okay? And that's going to help us solve this problem. So why can't this hold water? Well, if we poured water right here, it would all spill out the left side. Why? Because the left wall is not higher. It is not higher than the current square. Okay. So if the left wall is not higher than our current square, so let's say CS is current square, and we'll say if left is less than or equal to the current square, then no water. Like we can't hold any water because it's all going to spill out. But let's take a look at another square, okay? Let's look at what would be a good example. Maybe this guy, okay? Or if you're looking at this part of the screen, this area right here, okay? If we're on this one right here, well, the left wall is higher, but can it hold water? Well, no, because the right wall is less than or equal to. So we'll say if right is less than or equal to our current square, then we can also hold no water. So these 2 facts can be combined into one statement. And what would that statement be? Let's use orange. So if our current square is lower than the left and right, then it has the potential to hold water. So if the current square is less than left and current square is less than right, we'll just put a smiley face because there's potential for it to hold water. And not just potential, there's a guarantee that it's going to hold some water, at least one, right? So now what we just did is we were comparing to the immediate left and the immediate right. But as we can see here, or in the example here, we're not just comparing to the immediate left and the immediate right. We're comparing to like the maximum on the left and the maximum on the right. So we know now that we need to keep track of the max height on the left and the max height on the right. And if those are both higher than our current square, then we can hold some water. So that's kind of step one of this algorithm, right? We have to keep track. Let's go blue. This is hard to see, but I'm going to do it anyway. Nope, sorry, that's too much. That blue, you're fired. Get out of here. Keep track, there we go, of max left and max right. We know we have to keep track of that. And that's going to tell us if we're going to be able to hold some water. Okay, so now we have like a basic understanding of what we're going to do for our algorithm here. So let's pull up another example. Okay, let's do one that is just easy peasy lemon squeezy. Now I'm just going to pick a color at random for our new walls. And let's say we have one that looks something like this. Okay, so we got our lines. And then let's start with a really big left wall. And then let's kind of go down to here. And then let's just go right back up. Okay. And I'm going to kind of mark lines here so we can see. This is not good. I'm sorry. It's just the way it's got to be. Okay. So these are our walls. So we can just see how high each one of them is. Now let's grab, before we get into the pointers, let's just walk through this once just to see what exactly we're going to do here. So we know that at the left and right, we can hold 0 water. So we're just going to put zeros here. Okay. So let's start keeping track of the max height on the left and right. Now this one is clear to see that the max height, well, they're both the same, and they both happen to be at the edges. So we'll say max left equals 3 units, and then we'll get a white one here, max right also equals 3. And we're not even going to update those in this example, so those are just going to sit over there. So how do we figure out how much water this square can hold? How do we figure out how much water this square can hold? Well, we know the max is going to be involved, right? And since they're the same max, we don't have to worry about which one we're going to choose. So we'll say the maximum that this could hold would be what? Well, it would be 3. Okay, so we're going to say that the amount that it can hold is going to be the max, so 3 minus something, right? Because it's going to be 3 or less. It can't be greater than 3 because we can't dig holes down here. We're not hobbits. So we're going to subtract it by the height of the current square, which happens to be 2. So 3 minus 2 is 1. So we can hold 1 unit of water here. Now, I think you see where I'm going with this. So now let's go to this square. Okay, the max is 3 minus the current square, which has a height of 1, which equals 2. So we got 1 square here and 1 square there. And then here we also have 1 square. So we can hold 4 units of water in this thing. Now, let's do another one. Let's change it up just a little bit for an example. So we're going to start the same way. So we've got 3 here. And then we've got, oh God, this is not good. 2 here. This is not to scale. 1 here. And then let's say here, it only goes back up to 2. Okay. So this one's going to be a little bit more interesting. So our max left equals 3. And our max right, which we did in white, rhymes, equals 2. Okay. So now, if we're looking at square, once again, that's right, our edges can't hold any water. But we're trying to figure out how much water this guy can hold. Well, we can't hold, you know, they say like a chain is only strong as its weakest link. Well, this pool, it can only go as high as its lowest wall. So the maximum we could hold here would be 2, right? Because the max right is 2. It can't possibly go any higher than that. So what we're going to do is we're going to say 2 minus the height of this one. Okay, and I hope that makes sense. We can't go higher than 2 because our max right is 2. So we can't go any higher than that. So 2 minus 2, of course, is 0. Right? Can't hold any water there. And so now we'll go to the next one, and we can just tell by looking at it that can hold 1 unit of water. So what we did here is we didn't compare the square in our problem down here. We didn't go to like, oh, well, this is closer to the left wall or it's closest to the right wall. What we did is we took the minimum of the max left and the max right. And that's the highest wall that can hold water. I hope this makes sense. I'm going to grab, let's just flip this over, and we're going to start going through with our 2 pointers. Okay, so bear with me here. I'm going to do some setup. We're going to switch to stop motion and have some fun. So I probably should have laid the paper landscape instead of portrait. I wanted to do the first example from Leetcode, but I ran out of space, so we're just going to cut it down a little bit. We're going to set our pointers here. We'll have a left pointer in blue, a right pointer in pink, and we're going to start at the beginning and the end of our array. We're going to have our variables, our max left and our max right. And then for our algorithm, we're only going to do 3 things. We're going to move a pointer, we're going to update a max, and then we're going to update our result. So I should probably have a result variable. We'll call it res. Okay, so let's go through this algorithm. Our current max left is going to be set to index 0 of the array. And then our max right is going to be set to index length of the array -1, so the final value. So we're actually going to start our pointers at the end. Now remember, we said that those cannot hold water, but hopefully as we go through this you'll understand why we put them there. So let's go ahead and check. We are at index 0. The value is 0. So we're going to take the minimum. Well, okay, I lied. Let's actually go through the 3 steps that I put here. So the first thing we're going to do is we're going to move our pointer. So which pointer are we going to move? It's kind of arbitrary. So what you can say is something like, okay, if the max left is less than the max right, let's go ahead and move the left pointer. Or you could say if the max left is less than or equal to the max right. It's not super important, but that's the way we're going to do it right now. So is the max left less than the max right? Cool. So we're going to move our left pointer. Now we're going to update our max. Okay, so our max left was 0. The value is 1. So we're going to kick that 0 to the curb, and we're going to make the new max left 1. Now we can look at updating our result. Remember how we decided we were going to do that? We would take the minimum of the max left and max right, so 1, and then we're going to subtract from it the height of our current square, which is 1. So we don't do anything. All right, and we moved a pointer. And so now we're going to go ahead and do it again. All right, so is max left less than max right? Well, yes, it is. So we're going to move the left pointer. Okay, so now we're pointed at 0. Now, do we need to update the max? Is 0 greater than 1? No. Well, let's try to update the result then. What is 1 minus 0? Well, it's 1. And we can see that we can hold, I want to say a square of water, but it's obviously a rectangle. So, sorry. The result is going to get incremented by 1 because we can hold 1 unit of water in that square. All right, let's keep going. Let's move our pointer. Well, is max left still less? Yes, it is. All right, well, let's move our left pointer. Do we need to update the max? Well, yeah. The value 2 is greater than 1. So let's get rid of that. Put our 2 in here. Now, we updated the max. Now we're going to update our result. Well, we see that 2 is the same as max left and max right, so we know it can't hold any water. So now that max left is no longer less than, we're going to move the right pointer. So, okay. So the max right remains 2 because its value is 1. So we don't need to update the max, but can we update the result? Well, yeah. 1 is less than the minimum of these two maxes, so 2 minus 1 is 1. We can increment our result by 1. So we're at 2. Now, is max left less than max right? Well, no, it's not. So we're going to move the right pointer again. Do we need to update the max? No, we do not. Can we update the result? Well, 2 is equal to 2 and 2, so it can't hold water. So once again, we're going to move this right pointer. Now it's pointing at 3. So it is greater than the current max. So let's update our max right pointer to 3. And so now we see that 3 is higher than the lower of the two maxes, so we know it can't hold water. And now we're back into a state where the max left is less than the max right, so we're going to move our left pointer. All right, now we're pointing at 1. We move the pointer. Do we need to update the max? Is 1 greater than 2? No. Can we update the result? Well, let's see. The lower of these two is 2. Minus 1 is 1, so yes. We can update our result to 3. We can now, between here and here, hold 3 units of water. So max left is still less than max right, so we're going to move our left pointer. Now we're pointing at 0. Okay, so we moved the pointer. Do we need to update the max? 0 is less than 2, so no. Can we update our result? Well, the lower of these two is 2. Remember, that's the shorter wall. And the value is 0, so 2 minus 0 is 2. Whoa, we can update our result by 2. So now we're holding 5 units of water. So max left is still smaller. We're going to move it, and now we're at 1. We move the pointer. Do we need to update the max? 1 is less than 2, so no. But can we update our result? Well, the lower of these is 2. Minus 1 is 1, and so we can update our result to 6. Now, if you noticed as I was going through this, we're using a while loop. I didn't say that we were going to increment 1 pointer by default. We probably could have used a for loop. I just decided not to in this instance, but you can do it however you want. I wish you well. So now that we've gotten to the point where the left pointer is touching the right pointer, we break out of our loop. So now let's just go ahead and move over to the code. Now let's see if I can do this without making it. Okay, so now we're back to the Leetcode IDE. And let's see if we can write some code here. Let's see if we can go ahead and write some code that will show the computer how to walk through that algorithm we just did. So if you recall, we had a couple of pointers. We had our left pointer, which we're going to set to 0, so the beginning of the array. And our right pointer is going to be the length of our array, which is called height, minus 1, so the final index of the array. And you might be asking yourself, which I used to all the time, why don't we put -1? Why don't we do that? Well, if you think about when we're doing a while loop, we're going to say while the left pointer is less than the right pointer. So immediately it wouldn't do anything because 0 is not less than -1. And also it's harder to determine when they cross paths. So this way, yeah, you'd have to add a couple extra letters. You can go ahead and submit overtime for that. I think we'll go ahead and pay that. So we've got our pointers. Now we need to set our max left and our max right. So remember how we do that? It's just going to be the edges are going to be our current max. So max left is going to equal height at our left pointer. And max right is going to be height, our array, at our right pointer. And we're going to start a res variable for our result. So, like I said, we're going to have a while loop. So while the left pointer is less than the right pointer, we're going to do our algorithm. Remember, there are 3 parts. We're going to move a pointer, we're going to update the max, and then we're going to update result. Now, the reason we're moving the pointer first, the reason we're able to do that is, remember, we can't hold water at the ends, right? And if we wanted to start from where we can actually hold water, we'd have to start at index 1 and height -2. But then if the array was, short, right, we might be starting at this. Anyway, there's a couple of edge cases that we can avoid by doing it this way. So we're going to go ahead and we're going to move our pointer right away. But we have to know which pointer we want to move. So we're going to say if the max left is less than the max right, we're going to go ahead and move the left pointer. So we're going to increment it by 1. Then what were we going to do next? We're going to update our max. So we're going to update the max of the pointer that we moved. So we moved the left pointer. So we're going to see if we need to update the max left. Okay, and I just realized I did not put an equal here. So before that fails, let's go ahead and fix that. So the max left is going to be set to the maximum of the current max left or height at our new left pointer after we moved it. Then we're going to take our result and we're going to see if we can increment it. So we're going to do max left minus height at our left pointer. All right. Now you might be saying, well, what if the place we've got to is higher than our max? Well, that's why we updated the max first. The order of these is very important. If you switch these, it ain't gonna work. So now, if we decided that we want to move our right pointer instead, and the case would be the right pointer is less than or equal to max left, we could just do else here. We're going to move our right pointer. We're going to decrement it by 1. Then we're going to update our right max, just like we did to the left. We're going to set it to the maximum of the current max, or the height at the new right pointer. And then we're going to go ahead and update our result. So res plus equal max right minus the height at the current square, which is the index of our right pointer. And that's it. That's it. We're just going to be checking each square versus the max left and right. Because remember we said pool can only hold up to its shortest wall. Shortest, like, you know, the chain, strongest, weakest link. Oh my God, I need more coffee. And then all we're going to do is return our result. Now, let's do a quick look to the Leetcode gods and see if they're happy with our work. Let's run this, see if I made any syntax errors, which I am known to do. Okay, and I did. There's something going on here. So, max left is, I said greater than. Let's try less than. There we go. See, you just flip this thing backwards and it all goes to trash. So if we look at our space complexity, we are not using any additional data structures. So that's right there. It should be constant space, which is nice. And we're just iterating through the array a maximum of 1 time. So we should be big O of n time complexity, which is pretty cool. If you can solve a quote unquote hard problem in big O of n, I think you're doing all right. So I hope this was helpful. I haven't done a video in a while, and I certainly did not feel like doing one today. But sometimes you just got to suit up and show up, and then things can start working.